Hello, linear algebra student. This video is for chapter 4.6 rank, and this is the first video for 4.6. Rank is a new term, so let's define it. What does it mean? Rank of A is the dimension of column space of A. So dimension of column A is just another name for rank. We already know what is column A. Column A are the space formed by linear combination of all the columns of A. So column A is actually the span of A1, A2, or AN vertically, right? But they are not linear, they may not be linear independent, so we can do a REF to figure out which of them are linear independent and get the to form a basis. We'll do an example later. But if you want to review it, I think it is covered in either 4.1 or 4.2. So for example, let's do an example. Dimension is how many dimension is the number of vector in the basis. So if any vector, you count the number of vectors in the basis, that is its dimension. For example, B is a REF of A, and when it is an REF, the columns are in independence. The prefix columns are independent, not all the columns. Prefix columns are independent, and these are actually the position in A where the column space are. Now, these are not the column space basis. It is position column 1, column 2, and column 4 in the original A would contain the basis 4. So in column A, the basis would become, so you would just do A1, A2, and A4. So the third one you throw away because it's depending on the others. So that's how you find, and because it is 3, so dimension is equal to 3. Dimension of column A is equal to 3, and we say rank is actually the dimension of the column A, so it's 3. So in this case, 3, 3. What about now A? Now A is the free variable, number of free variable. In this case, we have one free variable in the now, x1, x2, x3, x4. So it's 1. Okay. This is old stuff in 4.3, I think. 4.3. New terms and new vector space. So there's something called a row space or row day. Okay, we shorthand it to write it row day. So if you have a m times n matrix, we can form a vector space horizontally, identify row as a vector. Now, when you write row as a vector, we write it in horizontal like this, like A11. The first row is A12, etc. A1n. So this is one vector, a vector in row day. And because they have n entry, so it is part of Rn, but I think written in a horizontal form. So our row day is a subspace of Rn because it's a linear combination of rows in A. A transpose, the rows become columns. So column of A transpose is actually row day. They are part of subspace of Rn. So anytime we have a vector space or a subspace, we want to find the basis and figure out what the dimension is, right? So let's look at theorem 13. So in theorem 13, we talk about how to figure out what the basis for row date is, because all these rows is, for example, this is the original A, this is the REF of A. So obviously they might not be independent, we're not sure. So how can we figure out if they are good for basis, or is this a good basis? So the idea would be, if we think about row day, which is just a linear combination of the row together, it is almost the same as we do a elementary row operation. When we do elementary row operation, there's 3 activities that we do. We scale it, which is a linear combination of rows, we swap things, which is nothing. We also can multiply scale a vector and add to another vector. That's just linear combinations of vectors. So we can say if you have two vector A and B and they are row equivalent in any form, then their row space are the same. And in particular, if B is in echelon form, like in this case, why do we choose echelon form? Because when vectors or when rows are in echelon form, each rows must be independent of each other. You see how the first row has a prefix column. This prefix column entry cannot be done by linear combination of the rest of the one below it. The second one can never be a linear combination of the last row. So all these rows are independent. And all of a sudden, because the spaces are the same, and these are in the linear independent one, so the REF form of a matrix, the individual row that has the prefix position, of course, only those of the prefix position, become, or the non-zero rows, well, if it's zero, that doesn't make sense. These three rows become the basis for row A. So we don't go back to row A, but these three will be the spaces for row A. So look at this example. What are the row vectors of A? The row vectors of A would be, row vectors of A's are these three. You only have this -5, x, 0. These are the three row vector. -5, 1. We write it this way. And the third vector is the third row, 1, 7, -13, 5. You see, we don't write it vertical. We don't use the square bracket. We just use this curved bracket. And what is the subspace spanned by this? So this would be just a span of this three row vector, right? -2, 5, -5, 8, 0. Just say spans. Spans means linear combination. 1, 3, -5, 1. Now, these vectors are they belong to R4, right? But just written in a special way. But I am when I span this, it would not span R4 because I only have 4 bases, or well, I don't know if they were bases. If I only have three vector, I cannot span R4. So what are the bases for row A then? For row A, like what I said before, you use the REF form and look at all the prefix position in each row. The run with the prefix position, that means the non-zero prefix position rows, become the basis. You pick the ones. So basis for row A would equal to this three vector, -2, -5, 8, 0, which is actually the first row, and then 0, 1/2, -1, 1, and then 0, 0, 0, -4. So these are the bases because they're for 100% surely independent. What are the bases for column A? Basis for column A would be the three prefix column corresponds to the independent columns in B. So basis, so do not use the one that you have in REF, but go back to column 1, which is -2, 1, 1. Column 2, -5, 3, 7. From REF, we know that they're independent. The third one, 0, 1, 5. So this is the basis for column A. What about now A? Now A need more work. To find basis for now A, you need to do RREF. So do the RREF of either A or B, doesn't matter. B is faster because it's already that. So RREF of B, I have it in a decimal calculator. I put this over here. This is and I do REF of, this is actually B, but it labeled as A, so it's 1, 0, 1, 0, 0. 1, 0, 1, 0, 0. The next row is 0, 1, negative 2, negative 2, 0, 0. The last one is 0, 0, 1, 0. Right. So read this off. X1, X2, X3 is free, right? And X4. So we'll say X1 is equal to negative of X3. X2 is equal to 2X3. X3 is equal to X3, which is free. You can assign it anything you want. And X4 is always 0, because this is, for now A, we're solving AX equal to 0, right? And the solution of AX0 is this. So we can say REF of A or B. And we got that. So if you factor X3 out, the vector is negative 1, 2, 1, 0 times X3. So this is now A. Yeah, this is now A. Now A is a linear combination or any multiples of this. And so what is the basis then? After you find the span of it, the basis of now A is just one vector. The vector that you use for multiplying to the free variable of X3. X3 is real. Right, so this is the now A basis. Then the column A basis, very easy. Row A basis is also very easy. But the only thing difference is for row A's basis, you use the REF entries. You use the row. But for column A, you use the original matrix. So this is the warning that I say we only need REF to identify basis for column A and row A, but we need REF of A to find basis for now A. Notice that row A and now A has no relationship with entries in matrix A, but column A use entries in A. Okay. The rank theorem. So maybe I'll use the next video to talk about the rank theorem in the next page.